I'm Tamás, and now I present the paper Batchy, batch scheduling data flow graphs with service level objectives. This is a joint work with Felicián and Barath and Gábor. So, just a sec. We all have known for a very long time that doing things in batches is easier. When you wash the dishes at home, you probably wait until there is more than one spoon in the sink before you start washing it. Yeah, we've known the same is true in computing. Yeah, it's applied universally in hardware and software. Yeah, our modern systems rely upon this as they process data in stage after stage, passing along a batch to be processed by the next stage. So these data flow graphs implicitly operate on batches, and yet they do nothing to make this batch processing more efficient. Yeah, a trivial solution might be to simply buffer more and more and then process a massive batch all at once, like letting the dishes pile up in the sink and then washing everything at once. Yeah, but what happens to latency? It skyrockets. Our work, Batchy, is about getting both efficiency and low latency in batch processing. We focus on packet processing, but it generalizes beyond that. So let's consider batch packet processing in a directed acyclic graph. And for simplicity, let's consider batches of size 2. In this simple example, node A and node B are two interconnected processing nodes. And both of them can work on full batches with size of 2. Yeah, the packets are represented by those red hexagons. And node A, and what you will see is that node A processes a batch of 2 packets and then forwards the batch to node B. That works great. What we see here is the efficiency is at top. But what happens if A decides to forward each packet to B or C, and then each gets one of these packets? Now, B and C each have 1 packet batches. So each doesn't know when or whether they will receive more packets. So they will just have to operate on these packets without any waiting. Yeah, this is inefficient, since B and C cannot utilize all their capacity. A trivial solution, yeah, let's try it. So add buffers in front of B and C and fill up these buffers before giving B and C the packets. Yeah, so what we see is that we get the efficiency, but delay will predictably skyrocket. So we need to be able to choose the right buffer size for B and C. But to see the effects of massive batching, it would be more visible if we zoom out a bit and see what happens in a real-life software switch that works on a large number, at least 32 packets in a single batch. So given the same pipeline, increase buffer sizes and processing capacity starting from buffers of size 2. Now, we focus on delay, since we have already seen that massive batching provides a high efficiency, so consider it done. So as we see, we start to increase the buffer size and the processing capacity. We see that the delays slowly start to increase as we increase the buffer size. Another important thing is that the pipeline also faces a delay service level objective that we want to comply with. And as we see that we increase the buffer, wait more and more to increase the efficiency, and what we get is at that one point, as we increase these buffer sizes, the measured delay will hit the delay SLO. And that is a limit, since if we further increase the size of the buffers, the resulting delays will be over this required level. And this is a delay violation. So picking this, but actually, it seems easy. But picking that correct magic number for these buffer sizes is in real life hard, because traffic can vary. And worse still, each node in the pipeline, in the system, may have its own delay requirements. I mean, a robot control application needs low latency, whereas the logging system may not. So we need to monitor these nodes and also their needs and make real-time decisions to set the correct buffer sizes. And this is where Batchy comes in. Batchy aims for 2 things at once. First, to process as large batches as possible. This way, it can ensure efficiency and high performance. And second, it can provide enough resources. And second, it focuses to provide enough resources to prevent violating these delay requirements. Actually, it might seem that there is a trade-off here. But let me show how we achieve both. So It is a fact that every processing node is different. Yeah, we profiled a lot of them using Batchy's profiler. We found that, yeah, actually, I showed some results. On the x-axis, you can see the batch sizes in packets, and the y-axis presents the execution time that the node takes to process a batch. And what we have seen that there is this processing time has two main components. One is a non-negligible fixed cost of scheduling and running a node. And this other component is the processing cost of each packet in this batch. And processing large batches instead of single packets is best because it amortizes that fixed scheduling and running overhead. And the thing is that we have to be precautions, as we have seen, to prevent delay from skyrocketing. And to see which nodes can benefit from working on large batches, we needed a metric. Yeah. As you can see, a linear model fits our profiling and yields a metric we call batchiness. This is the ratio of processing n packets in one batch instead of processing them n times as a single packet batches. Yes, and as a very simple example, suppose it takes 1 microsecond to process 2 packets as a batch. And if we compare it to process it as separately as single packet batches, it takes 4 microseconds. Yeah, in this case, the batchiness is 0.25. But what batchiness means is if it's close to 1, that's a high batchiness. It shows that the node's execution time is not sensitive to the batch size. It means that buffering in front of these nodes is no real batch processing gain. But on the other hand, if nodes have low batchiness, that is close to 0, this has a significant performance gain. I mean, this node has a significant performance gain to work on batches. And we found that the commonly used routines tends to have small batchiness values, meaning it is beneficial to feed them with large batches. And actually, that's why we put a buffer in front of each node. But that's not just a simple buffer. We introduce a special buffer that we call a fractional buffer, and this fractional buffer has an extra property to the simple buffers. Its size can be set between 0 and the maximum batch size. And this size adjustment is atomic and results in no packet loss. Actually, if Nagel's algorithm rings the bell, that's good, because with this fractional buffer, we want to achieve something like that, to weight up some, but not a fixed number of packets. So the thing is recalibrating these buffer sizes at every incoming batch is not efficient, and is also questionably feasible. Yeah, so we tried formulating and solving an optimization version of the buffer size control, but actually it was far too slow. So as a solution, we implemented a one-step preceding horizon controller, and this controller has 3 main goals. The first, to limit the buffer sizes to keep measured delays below the required level. Second, to short-circuit the useless buffers that are either reserve large enough batches or would introduce either batch fragmentation or delay requirement violation. Actually, these steps improve the performance too. And third, to handle situations when buffering on its own is not sufficient to reach the delay requirements. In this case, Batchy migrates the heavy traffic flow to other workers, like, yeah, this means CPU cores. And this way, it provides enough resources to comply with the delay requirements. We implemented Batchy over BAS. This is the Berkeley extensible software switch. Yeah, mainly because we are quite familiar with it, but also it has good abstractions and great performance. We implemented a fractional buffer as a BAS module, and Batchy runs a separate Python process to instrument and control the running pipeline in BAS. The controller runs on a tight loop. First, it measures delays, packet rates, and batch occupancy in the whole pipeline. Using these variables, it does the math, and then sets the buffer sizes accordingly, or initiates a complete pipeline decomposition. OK, but what happens if the software switch does not support this fractional buffer? Well, we implemented an on-off controller that either adds a full-size buffer in front of a node, or it just short-circuits it. To compare Batchy with the baselines, we also implemented a null controller that does no buffering, and the max controller that sets all buffer sizes to the maximum size. OK, actually, it makes more sense to compare Batchy with the state of the art, and therefore we re-implemented NFV nice which is a state-of-the-art network function virtualization scheduler framework, over BES. Okay, we did the comparison to see, first, how bad is the batch fragmentation? And second, how effectively can Batchy mitigate that? For this purpose, first I'd like to present the results with the most vanilla use case taken from a 5G benchmarking suite. This is a basic IP router pipeline. The main component of the pipeline is a layer 3 IP lookup node. And group processing chains are connecting to the outgate of this lookup node. And these chains implement next step processing like MAC switching, IP checksum recalculation, things like that. And to make things even more vanilla in this measurement, we use a static traffic mix that is uniformly distributed among the next hubs. We set Batchy's delay requirement to the 80% of the measured delay of the max controller. This way, Batchy has enough space to defragment batches while facing a strict delay requirement. Okay, the controller kicked in every 100 milliseconds and was said to be aggressive in terms of the batch defragmentation. Okay, in this measurement, we were focusing on static state performance. And first, we see that batch fragmentation is common even in such small and simple pipeline and results in low performance. As you can see in the figure on the right side. And on the other hand, we see that batch defragmentation truly improves performance. And yeah, actually that works well with the max controller too. But instead of the max controller, Batchy was able to comply with the delay requirements. Yeah, if you see the figure, there is a small violation in it, but relaxing the aggressiveness of the controller solved this issue with in a cost of a tiny rate drop. But even so, with this tiny rate drop, we see that Batchy yields the highest throughput among all approaches, and this is thanks to defragmenting batches and short-circuiting the useless buffers. But it is rarely the case that the traffic mix is static. For example, see this complex telco pipeline. This is a full next-gen mobile gateway. This is a key component in a telco infrastructure. Actually, it interconnects the telco operator's internal network with the outside world. And as you can see in the figure, there's multiple levels of traffic splitters in it. And these splitters are the hotbeds of batch fragmentation. The pipeline first dissects the uplink and downlink traffic. And the traffic is then further classified by quality of service levels. These are services. And for example, there might be a service dedicated to voice over IP traffic that requires low latency. But there might be another service that focuses on bulk traffic like file transfer. Yeah, these are just best effort things, and they like to push as much as they can. So anyway, the last traffic classification level is at the level of users. So users may have connections. Yeah, actually, users have connections over multiple services simultaneously. They tend to connect and disconnect, and this results that the volume of traffic is varying. So in our measurement, we had 16 users over 2 services. One service was processing bulk traffic with no rate limitation, while the other service had a 1 millisecond delay requirement. And the volume of the delay-sensitive traffic varied in every 2 seconds according to the presented throughput pattern. We observed the following. First and foremost, Batchy was able to keep the delay requirements. Except some transients when the traffic slowed down. But actually, at every change, Batchy was able to correctly recalibrate itself perfectly in a single control period. Yeah, as you can see this in the figures of control values of an upstream processing module of a user on the delay-sensitive service, and the other figure is the delay measured on the delay-sensitive service. And also, thanks to Batchy, the whole pipeline benefited from massive batching, yielding a 3 times performance improvement. Yes, you can see on the pipeline throughput figure. And also note that Batchy is selective buffering, which means it was doing massive batching on bulk service and was cautious in buffer short-circuiting on the delay-sensitive service. It's not just sped up the whole pipeline, it also resulted in a very small measured delay that was on the delay-sensitive service, and this delay was even smaller than the null controller's measured delay. So we have seen that Batchy is able to operate on real-life scenarios with a great success. So actually, in many cases, it improved them significantly. OK, so as a final thought, Batchy can balance batch processing efficiency and latency in arbitrary graphs, even at standards of microsecond delay service level objectives and an MPPS scale throughput. And last but not least, Batchy is available as an open source software on GitHub. And thank you for your attention. Happy to take your questions.
Questions?
I gave some extra time. Come on.
So I have a question. So how did you come up with the measurement methodology that you guys had? Why do you think that's representative?
The measurement methodology?
Yeah, so you had 16 users, I believe you said.
OK. That's a typical small use case. I mean, it's a bit small, but yeah.
So, and then how do you expect your results to get affected as you have more and more users and the system becomes more complex?
We measured the effect of, we have seen that many factors are improving the, many factors are affecting the effectiveness of Batchy. And one thing is as the branchiness of the graph. I mean, there are multiple outputs in a splitter model, and there are many batch defragmentation. Batchy gets more and more better, and there is a higher gain if we see, more modules and more branching.
Thanks. So, any question?
Hi, Marius from EPFL. Great work. So you didn't talk much about how you map the different stages of the pipeline to different cores in the case of the software suites. But there's this notion of adaptive batching, which means that you run every stage to completion, and every time you go back, you take whatever is there and you finish that. So did you compare with this, with the adaptive batching approach, and do you have any idea how it would work in this case?
Yeah, actually, we're focusing in this work in a more like a single core, stuff like that. And later maybe we can build on a more complete framework using multiple cores and things like that. But actually, to answer your question, I haven't checked that stuff. But thank you for. Thanks.
OK, so let's thank the speaker.